Another aspect of inorganic chemistry that impacts living things would be that of acids and bases. And we're going to look at acids first. The question is posed here on the screen, what makes an acid acidic? Well, let's first of all look at the examples that we have listed on the left-hand side here. We have HCl, you'll probably know that as hydrochloric acid, H2SO4, which is known as sulfuric acid, and HNO3, which is nitric acid. Of course, what do they all have in common? They all begin with that letter H, which stands for hydrogen. That's the commonality, and that goes a little ways to answering our question there at the top of what makes an acid acidic. If we focus in specifically on the HCl just all by itself really is not hydrochloric acid. It only becomes hydrochloric acid if we take it and drop it into our flask here. And let's just assume that our flask is filled with some water. When the HCl goes into the water, what happens is something called ionization. In other words, ions form. An ion is a charged atom, and you can see next to the H is a positive charge, and next to the Cl is a negative charge. When HCl gets put into the water, basically it breaks apart. It breaks apart into the H and the Cl separately, but in doing so, the H loses its one electron and the chlorine takes it, and that's why the H has a positive charge. It lost its negatively charged electron, and that's why the chlorine is negatively charged, because it took that negatively charged electron. The chlorine in this particular example basically means nothing to us. In answering the question, what makes an acid acidic, the chlorine's presence is really of no importance. The answer to that question is really all about the hydrogen ions. What makes an acid acidic? The answer is hydrogen ions. The more of these you've got, the more acidic this particular solution will be. If we take that same approach and we look instead at our bases, what makes a base basic? Well, look at our examples here again. NaOH and KOH. What do they have in common? That's the OH, oxygen and hydrogen. Now, one of the things that's sort of a little background information here when we talk about bases is that there are some atoms that go together so frequently, in this case oxygen and hydrogen, that the combination of those two gets its own name. So we would not call this sodium, oxygen, hydrogen, the Na being the sodium, OH, oxygen, hydrogen. Instead, the OH, which is such a constant combination, or a familiar combination, we call that combination hydroxide. So this is sodium hydroxide, and this is potassium hydroxide. Same deal as with the acids. Sodium hydroxide all by itself is not necessarily a base. It only becomes a base when you put it in water. And when you put it in water, the same thing happens to it that happened to HCl. It ionizes, it breaks apart. And in breaking apart, again, the sodium loses one of its electrons, and the OH combination, the hydroxide, takes it. And so the hydroxide is negatively charged. This base that we have now formed here has nothing to do with that sodium. It's there, but it's not important in terms of answering the question, what makes a base basic? A base is a base because of the hydroxide ions that are floating around in the water. And the more of those that you have, the more basic this solution happens to be. So let's think back with both the acids and the bases now. One of those things that you probably learned when you were in elementary school is that all squares are rectangles, but not all rectangles are squares. Well, that same idea is present here as we talk about acids and bases. All acids have to have hydrogens, but not all things with hydrogen are acids. All bases have to have hydroxide, but not all things that have hydroxide are bases. The only things that are acids They have to have hydrogen, but they have to be able to break apart in water and form those hydrogen ions. All bases have to have hydroxide, but things that have hydroxide that don't break apart in water, they're not bases. Only those things that do break apart in water or ionize in water are bases. When it comes to being able to measure these acids and bases, you're probably familiar already with the idea of the pH scale. pH scale is a little odd in that it's based on 1 to 14 as opposed to, say, 1 to 10 or 1 to 100, but it goes from 1 to 14 and is a measurement of the acidity or basicity of any particular solution. If we look smack dab in the middle there, we have 7, which is neutrality. Something that has a pH of 7 is neither an acid nor is it a base. As we go down the pH scale, below 7, heading towards 1, we have acids. The further you go towards 1, the more acidic that particular solution happens to be. So maybe it's a little bit strange, but if we compared two solutions, and one of them, let's say, had a pH of 5, and the other one, let's say, had a pH of 2, the one with a pH of 2 is actually the stronger acid. Despite the fact that it's a lower number, it's the stronger acid because it's further away from neutrality at 7. If we look above 7, as numbers go from 8 through 14, anything in that range happens to be a basic solution. In this case, the higher number is the stronger base. So the further you get away from 7, the stronger that base happens to be. So pH of 13 versus a pH of 10, the 13 is the more basic solution. And what do those numbers really represent? They represent what we were talking about earlier. How much hydrogen ion or how much hydroxide ion is present in that solution. Notice at 7, the levels are equal. There's an equal amount of H's and OH's, and therefore we have neutrality. But as you work your way towards the left, from 7 down, the hydrogen ions outnumber the hydroxide ions. And so you have more hydrogen ions floating around in the solution, therefore you have a stronger acid. The other end, let's say at a pH of 11, you have more hydroxide ions than you have hydrogen ions, and therefore those hydroxide ions make that solution a basic solution. In addition, there is this idea of neutralization. Acids and bases will neutralize each other. So if we look at the chemical equation that we have up here, I have an acid, there's your hydrochloric acid, have a base, there's your sodium hydroxide. What happens in this particular case, if you would put those two solutions together, is a neutralization due to a double replacement reaction. Basically what that means is that everybody switches partners. The H, remember, is positively charged and the Cl is negative. The sodium is positively charged and the hydroxide is negative. So if things are going to switch partners, the positive from here will join the negative from here and vice versa. So Na being positive, Cl being negative, they will join each other and they will form NaCl, which is, by the way, simply table salt. And the H, the positive, will join up with the OH, the negative, forming this compound, which, if we rearrange it, is simply water. And so by doing that, you're essentially taking all the hydrogen ions and hydroxide ions out of solution, forming a water molecule, and therefore reaching neutrality, the 7 on the pH scale. Lastly, I have this chart here on the left because we do have to connect this to living things. So we're looking at a human body there. And it points out a bunch of different places within the human body where there are solutions that have varying levels of pH. You can see, for instance, in the stomach, the gastric secretion, you need to maintain a pH in your stomach of somewhere between 1 and 3.5. It's pretty acidic. Whereas in the brain, you want to very specifically maintain a pH of 7.1, or in your muscles, somewhere between 6.9 and 7.2. So these pH ranges, these acids and these bases that are present in our body, they're important. There's a reason that those areas have the pH in which they do, and your body operates and functions based on you maintaining that pH in a very consistent way, which I hope sounds an awful lot like the concept of homeostasis that you learned about earlier.